our individual scores to the variability of the distribution of the sample means. So if you draw a sample in a perfect world, that sample mean is identical to your population mean. The larger your sample is, the more likely it is identical to the population mean. However, that's not always true. So you get different samples, you get different mean estimates. So the central limit theorem means to relate the variability of these to be expected variability in those sample means to the standard deviation of the population by standard deviation of the population divided by the square root of the n of your sample. So if your sample is smaller, there's more variability in your means. If your sample is large, there's less variability, and it's more likely to be equal to the population mean. So by quantifying this hypothetical variability of your means, you can now utilize this standard error of the mean to characterize your distribution of the sample means. So if you do hypothesis testing, you're calculating the difference between your sample mean and your population mean. And then you standardize this difference as per your standard error of the mean, which is calculated as standard deviation of the population divided by the square root of the n. And by standardizing this difference as per your standard error of the mean, you're quantifying the probability of your sample mean in fact really being identical to the population mean. So you quantify the probability of the null hypothesis being true. And that's also where you quantify this then as p-value. And this p-value is, if this p-value is smaller than your predefined alpha, which is your critical values, right? So we have these critical values, which are based on an alpha. And this alpha, in most cases, 99% of cases, this will be set at 5%. So you have 2.5% in the tails of each side, which also essentially translates then into the confidence intervals. So, and this comes back to this set score of minus 1.96 and plus 1.96, which corresponds to 2.5% probability in the tails of your distribution of the sample means and the difference of these sample means to your population mean. And when you think about a confidence interval, so we went through that why it's important to always quantify this probability and to compare something using a confidence interval and always to pay attention to a distribution as a whole and not just to hypothesis testing and reject the null hypothesis, but you need to keep in mind the actual variability within your samples. But what it comes down with the confidence interval, you mean to define an interval within which you're 95% confident you contain your population mean. If you don't contain the population mean in your 95% confidence interval, in the context of hypothesis testing, you are rejecting your null hypothesis, because by that, per definition, your probability of the null hypothesis being actually true is smaller than 5%, which is 1 minus 95%. So it's 100 minus the 95%, right? So as soon as this is outside of the confidence interval, you know it's significant. So if you're not sure with hypothesis testing on the quizzes that you did it correctly, quantify the confidence intervals and just look at it empirically. Always map out the normal distribution curve, make sure that you understand the normal distribution curve, where your mean is located to the mean of your sample mean, and understand the confidence interval. Then you can automatically hypothesis test, just for yourself, to help yourself. Map it out, write a mean, write down the numbers, calculate the critical values, and confirm your thinking. Sometimes the hypothesis test alone is a little confusing in the way you're looking at it. So mapping it out and drawing it out makes it a little bit easier to digest. Yes?
So I was going to ask what you use actually for hypothesis testing. hypothesis testing, what are you actually doing? You're not doing the test with the curve.
Well, you're doing the test with the curve, but you're quantifying an actual set. So with the 95% confidence interval, you just see those critical values. You're calculating those two critical values, and you see it's outside. But with hypothesis testing, calculating the sample mean minus the population mean divided by the standard error of the mean, you're calculating the actual set score and the actual probability with which that null hypothesis actually still can be true. And if that's smaller than 5%, you're rejecting it. So hypothesis testing is just exactly calculating the set score and the p-value associated with it. Yeah? So the confidence interval is an interval estimate. It's calculated as the mean plus your set score. So this is 1.96 multiplied by the standard error of the mean. Or it's the sample, upper is plus the standard error of the mean multiplied with the set score, and the lower bound, because it's symmetric on both sides, is actually subtracting that set score multiplied by the standard error of the mean. It's just basically inverse of the set score, and we've calculated that. It's just calculating actual values, right? So that's the way you look at this and you understand it. So basically you have a mean of your sample. You have 47.5% to the left of your mean, 47.5% to the right of the mean. You have your critical values that are basically demarcating 2.5% to the right or 2.5% to the left. If your mean, your population mean is within those boundaries, you are accepting the null hypothesis. If it's outside, you're rejecting it with 95% certainty. So now we talked about confidence interval. We talked about hypothesis testing. Now let's go a little bit deeper into it. So we have a set score calculated that essentially is calculated as the sample mean m minus the population mean mu m. We're dividing this, so we're calculating this difference, and now we're standardizing this difference, and we're utilizing this to determine our associated p-value. Again, it's not a percentile, it's a p-value. It's a probability now. That was a very skeptical look. If you're only looking at the percentile and it's individual scores, then it's a percentile. Yep. If it's individual scores, if it's all individuals, all cholesterol values in the US, then it's a population. If it's raw scores. Here in this context, standard error of the mean, it's the distribution of the sample means. You're calculating one difference between your sample mean and your population mean, you get one number. And you assume that there's a distribution of the sample means, of these hypothetical sample means, that randomly thousands of samples that you've drawn, you think that there's a certain distribution of means that associates with the size of your sample and the variability of that particular marker in your population. And this distribution of the sample mean you utilize to now standardize your differences. And that gives you an idea of whether your hypothesis actually, your null hypothesis is correct, or you're rejecting your null hypothesis. So now there are certain ways how you can change this. And this is basically strongly dependent on the sample size. So if you think of the formula for the calculation of the standard error of the mean, so it's the standard deviation of the population divided by the square root of the n. That makes it strongly dependent on the sample size. The larger the sample size, the more likely it will reflect the population mean. The more likely it will have less variability. So if the sample size is larger, the standard error of the mean is going to be smaller. And that's a problem because now you're standardizing your difference by a smaller value. If you use a smaller value to standardize these differences, your set score is automatically going to be higher. That's a problem because you're more likely to reject your null hypothesis. If you do that, you may see differences that you shouldn't be seeing. So effect size means to circumvent this problem by basically using a standard deviation instead of a standard error of the mean, just to get an idea to only characterize this difference. Because hypothetically, when you just look at effect size per se, with the same variability, you basically get a larger effect size by just the differences, right? So it's more likely that you reject the null hypothesis of these two being equal if the difference is larger, right? So the difference, if you look at this formula, the difference, they're basically just two factors that are determining that Z score. The Z score of 1.96 will always result in a p-value of 5%. The two determining factors are here the difference, and secondly, the standard error of the mean. The standard error of the mean is highly dependent on the sample size, as we've heard. So this we're taking out by dividing it by the standard deviation, and we talked about this in last class. So you've seen that already, the effect size. But you can also change the difference. If you have larger differences, your Z score is going to be larger too, right? So basically, independently of the variability, differences do play a role in the determination of the Z score. So if the difference is large, more likely to have a significant p-value by having a larger set. Alternatively, you can also have less variability. If you have a market that has less variability and you're making comparison that there's less variability, this will automatically also make it more likely that you see a significant difference. So the effect size means to essentially circumvent that. So the difference further apart increases the effect size, smaller variability increases the effect size. And to make this a little bit more of an objective marker that is less dependent on the sample size, you're basically quantifying Cohen's d. And Cohen's d is essentially the difference of your hypothesis test divided by the standard deviation of the population. Because in the perfect world, the standard deviation is not dependent on the sample size. Yes? No. Z-score is the standard error of the mean. No, that's the standard error of the mean. Sigma m is the standard error of the mean. This is a standard deviation of the population divided by square root of the n. And this is how it becomes dependent to sample size. And that's the difference between Z-score and effect size. The Z-score is dependent on the sample size, whereas the effect size is not, if you calculate it as Cohen's d. And this is an important distinction because it puts the weight on the difference rather than the sample size of that sample you have drawn. And then you're characterizing your effect size by the conventions for Cohen's d, where a small is basically considered between 0.2 and 0.5, medium 0.5 to 0.8, and large is everything greater than 0.8. So that's the conventions of Cohen's d. Flagging this as a quiz questions. Any questions for effect size? It's basically adding a little bit of confusion. So I understand that, but essentially what it does, think of this relationship between standard deviation in population and standard error of the mean, two different concepts. So the Z-score essentially gives you a probability. And now you move away from this probability. The Z-score that you calculated is the difference divided by the standard error of the mean. Thereby you get a probability of this distribution of the sample means, and basically a characterization of this distribution around this difference that you've quantified between the sample mean and the population mean. Now you're putting the weight back on the difference by taking the standard error of the mean that is highly dependent on the sample size out of the equation, and you work directly with the standard deviation. And you put that weight on the difference again. One way, so why do you need effect size? You need effect size for various reasons. So if you compare two samples, this could be, for example, that could be in a randomized controlled trial, control versus intervention. So you need to understand this effect size, because the effect size is essentially it's kind of a way to quantify a treatment effect independent of the sample size. It gives you an idea of how strong the differences of the intervention were, unaffected by the sample size. So now this builds now the segue into meta-analysis. Well, basically a meta-analysis is basically the calculation of a mean effect size from different effect sizes from different studies. So that's a little bit of a more complex topic to discuss, because essentially you have different levels of scientific evidence. You have different study designs, prospective study designs, that basically give you a certain level of confidence in these results, or a certain level of weight of scientific evidence. The lowest level is retrospective study, where basically you take a hospital electronic health record system, you have data of over the last 10 years, and you take this data and you basically compare diabetics versus non-diabetics. That gives you some estimate what that signal could be. If you now, moving forward, you study all diabetics and non-diabetics in a prospective fashion, in some way or form you're interested in, you have a prospective study. That is usually better designed, and it's a higher level of evidence. You can also, if you test an intervention, you can now study a control versus an intervention group. That gives you the highest level of prospective study design. If you have several randomized controlled trials and you have different estimates of the effect size, you can put these individual results of each study into what is called a meta-analysis. And a meta-analysis is something that you do based on published data. So basically, you're interested in one particular intervention, you're interested in one medication, for example, antihypertensive medication or cholesterol lowering medication. You're interested how effective is this treatment. You get different estimates of the effect size, and you're going through the literature, you're making sure that you have all this data available that has been published on the topic, and you get those different effect sizes. And then you put it together in what is called a forest plot. So each of these studies have quantified the effect of an intervention. And these effects are then put together in one analysis that is now characterizing a mean effect size. It's not really as easy as a mean effect, but I spare you the details on it, because there are very sophisticated models that basically take into account each individual variability of the respective studies. But it gives you one amalgamated estimate of the effect size based on the published literature. It's actually not as easy. It's also identifying this literature. You also do a risk of bias assessment. So it's actually quite complex what you do with this data. But essentially, this is what needs to be remembered. It's an amalgamated, aggregated estimate of the effect size of a specific intervention based on multiple published studies. That's a meta-analysis. So now all these studies have now a certain kind of effect size that is essentially greater than 0, right? So 0.2 to 0.5 is small, 0.5 to 0.8 is medium-sized, greater than 0.8 is a large effect size. So this effect size would actually be remarkably large. So now you also may have studies that are not showing an effect. So this study would basically change your overall estimate towards null. So it would basically lower the estimated overall effect size. This being said, if you have, so here you have 7 effects, and the studies was quite a good effect size. You have one that's a little slower, but the other ones are basically all greater than 1. So if you have now, in comparison to the 7, you have, let's say, 10 studies that showed null effect, that will almost like put your effects as so small that you wouldn't even think of an effect anymore. So therefore, you would conduct the so-called file drawer analysis. So the problem with many of the studies is when they're negative and they didn't show an effect size, they're not being published. So they end up in a file drawer. So a file drawer analysis is how many studies would you have needed to tank in a file drawer, put in a drawer and never publish to essentially get this result that you've seen, this effect size that was considerably large, towards null. So you estimate the number of null studies or non-published studies that you would have needed to get this a meaningless effect size. So that's a file drawer analysis.
Get a meaningless effect size?
Or a non-significant
Why
effect
is it
size.
not meaningless effect size?
No, you don't. You just estimate it. It's a hypothetical example to estimate, okay, so how strong is my insight?
You don't want your effect size to be not significant.
Well, you want in research, you want is a very problematic statement.
The researcher would like the experiment to show significance.
That is true, but that essentially, that's by its own right already points towards so-called publication bias.
Yeah.
Because, and that's where it comes down to, you remember that graph with the higher incidence of publications that had a set score of 1.96? That is basically a publication bias, because people want to publish something that is significant, which essentially may lead them to accept the type 1 error. And that's a problem, because a lot of research goes into trying to kind of prevent the population from actually suffering from erroneously considered significant treatments. So it's actually, for the safety of patients, it's actually important to identify whether there was a type 1 error. So this is why it's important to always replicate and reproduce study research.
How do you estimate this number?
Well, that's a simulation study. So you need to simulate how many papers you would need to have. So if you, for example, if you develop a model that takes these studies into account with their mean effect size, their actually effect size in the respective study, and then the variability, you would need to add a null entry to the model. So you would make additional rows and you would run the model over the rows with the 0. And there are algorithms that you can use. There are functions that you can use. R actually has some pretty good packages for that. So that's the file drawer analysis. And that gets us lastly to statistical power. And power is important because you remember when we accept something that should not have been accepted as a null hypothesis, as so-called false positive. So you reject your null hypothesis, but you shouldn't have rejected it. But you rejected it because you took a certain subsample, or you removed a couple of outliers, and you commit a type 1 error. That's a false positive. If you are not rejecting the null hypothesis, although you should have rejected it, that's a type 2 error. So we have a type 1 error and a type 2 error. The type 1 error, we are basically committing when we are finding a p-value that is smaller than our alpha. So the alpha is the determination of this critical value, which is 1.96 in most cases, right? Minus 1.96 and plus 1.96. So the alpha basically determines our maximally acceptable type 1 error. So the type 2 error is a little bit trickier because it is basically the so-called beta. So you have an alpha and a beta. The alpha is the type 1 error, the type 2 error is the beta. So this is basically where you have a true effect where the null hypothesis would be false, but you basically in your analysis you fail to reject this null hypothesis. And that's a type 2 error. And the number one reason for this to happen is besides wrongly conducted or poorly conducted research, the number one reason for this is an inadequately small sample size. And that's what makes it tricky, because you need, prior to each prospective study that you do, every randomized controlled trial that you conduct, you need a sample size estimation. You need to estimate how many people do I need to study to essentially see a significant effect, if there is one. You're basically going back to the literature and you're looking at the literature. Okay, so what did all the other studies show? You do a meta-analysis of what has been published so far. You have an estimate of your effect size. And based on this effect size, you will then also estimate your variability around this effect size. And based on this variability, you will use a formula to actually estimate what sample size you will need. And this will determine statistical power of your analysis and of your study. So basically, there are 4 different ways, and I'm flagging this for the tests. You have 4 ways to basically prospectively affect statistical power. Firstly, you can increase your alpha, because if you are willing to accept, bless you, if you're willing to accept a larger type 1 error, you will automatically more likely reject your null hypothesis, right? But it's a debatable approach. You can turn a 2-tailed hypothesis into a 1-tailed hypothesis. We're going to do this in calculation today, but you remember from the hypothesis testing chapter that there are basically problems with that, because if you use the p-value on both sides, you're creating a set score that is basically larger, and you hypothetically are less likely to reject a null hypothesis. If you do a 1-tailed hypothesis, you essentially you put your weight only on one side, and you're more likely to reject the null hypothesis. And we will do the exercise today where you're going to see exactly that. You can also increase your sample size, and this is the sample size estimation I was talking about, because if you have a larger sample size, your calculation of the standard error of the mean for the hypothesis testing will essentially result in a larger set, but lowering your standard error of the mean estimate. You can also exaggerate the mean difference between the levels of the independence variables. So when you have a control group versus an antihypertensive medication, you could increase the dose of the antihypertensive medication. You could intensify the intervention in some shape or form as possible. Obviously, this is not always possible, and this is not always ethically acceptable, which is the next problem. So all of these have to be taken kind of at a price. So you have on the following, you have a visual depiction of these approaches. So now here you have 5%, right? If you are looking for an increase of the alpha, you're basically accepting now a larger area. So you basically have this area where the 2 graphs are not overlapping, but this is being the threshold. That's your alpha. This is basically, this is your leftover power. This is the true power of your intervention, the true statistical power of your hypothesis test. So an increase of alpha is quite efficient to increase your power, but it's very debatable. Then you have a 2-tailed versus a 1-tailed test. So if you have 2.5% on both sides, and you're basically putting now 5% on one side, you essentially also increase your power. The problem is you will have a lot of backlash from statistical reviews using that approach. Thirdly, and the most efficient one, is by increasing the sample size with the same difference. So you're lowering the variability and you're solidifying that mean, that sample mean. Thereby, you decrease variability and you get a more accurate estimate of your sample mean. This basically will minimize standard deviation, the variability, and thereby allow for you to make a more accurate estimate. And then you can also increase the difference between the means, and you see this reflected here, but basically this difference being larger, thereby increasing the power between those two groups in the comparison of these two groups. And so now that's the thought experiment. So why is this actually important? Well, think about it. Because if you think about it in much detail, you spent $5 million from the NIH to conduct a large-scale randomized controlled trial over the entire US, and you did inaccurate sample estimations, and you end up not finding significant difference because you didn't study enough patients, and you concluded the study too early. You basically wasted that taxpayer money. And that is true for every source of funding you have. So it's super important to really understand the sample size you need to study to minimize that type 2 error to the furthest. So essentially you have statistical power is calculated as outlined here on this table. So you have here two different scenarios. You have in truth no effect, and you have here the second scenario, in truth there is an effect. The sum of these are basically 100%. If you make the correct decision to not reject the null hypothesis, you make a correct decision. This is 95%. If you accept type 1 error and alpha 5%, this is 5%. If this is again 100%, this is the power where you have an effect and you will reject the null hypothesis. This is your power. And then you have the type 2 error, the beta, where you have an effect, but you fail to reject it because you didn't study enough patients. This type 2 error should be not larger than 10% or 20%. In really rigorously designed, well-funded studies, it's usually 10%. So that gives you a power of 90% or 80%, depending on beta. So that's basically important to keep in mind. So the probability for this is 100%. So you either make a correct decision or you make an incorrect decision. 5% should be your alpha. And here it's 10%. And that should be to give you a statistical power, which is 1 minus 10%, which is 90%. Quiz question. Flagging. Okay. Okay, so you can increase your alpha, you can turn a two-tailed hypothesis into a one-tailed hypothesis, you can increase your sample size, or you can exaggerate the mean difference, which is often not possible. Okay, any questions? Personally, for me, for my understanding, to determine type 1 and type 2 error, this table is a very, very powerful table. So I'm flagging this table for me. Good. Any questions? If not, let's do a little bit of Excel. And then lastly, so we have until 5:55, correct?
Yeah.
So that gives us 33 minutes. Okay, good. So we have a practice lab. So it's a very simple exercise essentially. It is basically putting it's basically doing an exercise which we have done in the past. So we have a set test. We have a sample of 50 people. So our sample size is 50. We have conducting a set test on a sample of 50 people for whom you observed a mean verbal score on the SAT, a university admission test used in the US and other countries of 542. So in your 50 people, you have a sample mean of 542. N is 50. So we have. Yes, please open the R code as well. We're going to do this right after. No, you don't need to hand in the Excel. I will post the Excel actually later once we're done. So we have a mean of 542. We have a sample size of 50. Yes, I'm trying to make it as large as possible. Okay, so mean of 542, population mean mu is 500. And we have a sigma of 100. So this is pretty clear, right? So we have a clear understanding what we need to do. So first, yes. So we have in our step 1, so we're characterizing the population, we're understanding there's a sample size of 50. I know. I wish this were a little bit larger. Well, okay, so in step 1, first we need to understand the population distribution, right? So we're studying a sample of 50 people, we're comparing the sample now against our population mean, which is 500, right? Simple. So the first thing you need to do at this point, you need to now understand, okay, what do these distributions look like? So firstly, you need to quantify your standard error of the mean. So that's where everything starts, right? So the standard error of the mean here is the standard deviation sigma divided by the square root of your sample size, which is square root of 50, right? Yeah. Divided by, yes.
I did not get that.
Well, we can unfortunately not wait. I will post the Excel later. Okay, so we have a standard error of the mean of 14.14. So now next, what we need to understand, the formula is right there. We need to carry on. We don't have the time. I'm sorry. So now next, what we want to understand, we want to determine, okay, what's our critical value? We're doing a two-tailed hypothesis test. And we're determining an alpha of 5%. So our alpha is 5%. So we know this corresponds with a set score of minus 1.96 and 1.96 and plus 1.96, correct? So we know that. So this is our critical values. So we know this will be what we are looking at. Then we know in step 3, we need to determine now the actual critical values as scores. And this is, we're doing this as we always did, by basically,
Is that a Z?
yes, that's the C. We're calculating now our confidence interval, and we're doing here a lower limit and an upper limit. So the lower limit is basically 1.96. Oh no, let's do first. Mean equals our mean, our sample mean minus 1.96 multiplied by the standard error of the mean of 1440. So now we're calculating next. So next we're calculating the upper limit, which is basically our mean of 542 plus 1.96 multiplied by the standard error of the mean. That gives us the upper limit. So now when we just look at these two formulae, when we just look at this, so the formula right here. So when we look at these two formulae, what we're seeing here already is that based on our sample, the variability and the 95% confidence interval does not contain our mu. Based on that, we know already that is gonna be significantly different between sample and population mean. So now we want to put this into practice. Now we do step 4. We calculate our actual set. And we know the set is calculated by our mean, 542, minus our mu. So this has to be put into parentheses. Don't forget that, please. Divided by the standard error of the mean. Yeah. By the standard error of the mean. So that gives us a set of 2.96. So, but now we skipped one step, right? The step that we skipped, so I went a little bit far ahead. So step 1 is, what is our null hypothesis? What is our null hypothesis? The null hypothesis is M equals mu. That is, well, this is the calculation of the set score. Is basically done as B2 minus B3 divided by F3. So step 1, null hypothesis M equals mu. Step 4, this is null. So our research hypothesis, alternative hypothesis, is now M, and now this becomes a two-tailed hypothesis. In the two-tailed hypothesis, we only say like it's unequal to mu. So I'm using here something that is being coded, M. So this is coding language. So you do an exclamation mark on the equal sign that basically gives you unequal to mu. So this is basically a two-sided test, right? So it's basically, it's just telling you it's outside of the confidence interval. And this probability we're quantifying here with our set. So now what's the set associated with a set score of, what's the P associated with a set score of 2.96? For that, we go in the t-score table. No, not t-score, sorry. Set score table. That's the C value, yeah. So where's set score table? Yeah, so set score table. So 2.96. 2.96 essentially corresponds to a p-value of 0.0015.
But isn't that negative?
Yeah, that's negative, but you want the tails, right?
Yeah.
So it's symmetric. So whatever is there has to be 1 minus this is then this side, right? So you basically have minus 2.96 gives you 0.0015. So your P is 0.0015. That's your P. So this is substantially smaller than your alpha of 5%, right? So now, what is your conclusion based on that? It's significantly different. So you are rejecting the null hypothesis. So this is two-sided. So a test which we have so far not paid enough attention to is the one-sided test. So now that we do a one-sided test that basically is directional now. So when you have a one-sided directional test, the formula for your set is essentially m minus mu. That means m minus mu. That means if your mu is larger than your m, automatically this difference has to be negative, right? So it's you're basically you're looking at the left-sided hypothesis test. So if you say, okay, so we do a left-sided hypothesis test, we're concluding now under the research hypothesis that mu is larger than the mean.
It's not in our case, right?
It's not. But what is now our null hypothesis? Our null hypothesis is that the mu is smaller or equal our mu, our m. So mu is smaller or equal to m. So it's the opposite, right? So there's only, it just can go in either direction. Yes.
Going all the way back to this top by step 1, for some reason I got like my numbers are a little bit off.
Yeah, that's fine. I'll post the Excel sheet. We can't troubleshoot right now. We're a little bit in time crunch. I only have 20 minutes to get through there. I will post the Excel sheet later. Yes.
You define mu.
Hmm?
You define mu.
Population mean.
Okay.
Yeah. Okay, good. So the m, we know the m is greater than the mu. So we're testing this hypothesis now. So we're calculating again the very same formula, which is our mu, our mean, minus the mu divided by our standard error of the mean. So this is now again 2.96. So, but now essentially we're really looking for 2.96, right? So we know that our mean is actually much smaller. So if we're going now back to the table and we're going to plus 2.96, and this is why it's important to actually map it out, because that makes you understand it's left-sided. If you do two-sided, you just want that little tail. If you say it's left-sided, you're actually looking at the actual value. So 2.96 essentially you will find here. Here. So 0.9984. 0.9984. Correct. Because this is substantially larger than your alpha.
Wait, can you look at formula?
Yeah.
How did you know that? How do you know again when it's negative and when it's not? How did you know you were going to the positive side?
Well, for two-sided test, you consider both sides, right? So you just want those alphas. So you need to take that little one. You just need that little rest of the alpha, and you multiply that by 2 for two-sided. So you take 1 minus this p-value, gets you that alpha on the side. But you need to multiply it by 2. Actually, that's what I not did here. It was actually, thanks for reminding me. So you actually need to multiply this by 2.
Why?
Because it's a two-sided test. So you need to multiply this p by 2. Hmm? Yeah, yeah.
Can you explain again how you got the 0.9984 number?
From the set score table. So we know it's 2.97.
Yeah.
And that's here at,
It's 2.96.
it's actually 8 first. So here, this is 2.97. Right? 8, 6. Because now you're only interested in one direction and you're only interested in everything that's slower. If you do the inverted now, if you do right-sided now, you basically, your alternative hypothesis is that your mu is actually smaller than your mean. And this is now mu is smaller than m. Your logically null hypothesis, the inverted of that research hypothesis, is mu is larger or equal to your m. And now you're calculating again a set. You get the same set, right? This is exactly the same number.
What is this? Oh, this is right.
So now you have the same set, but now the angle at which you're looking at, because now you're only interested in everything that is above. So now you have 2.97. What's 2.97? It's a 0.9985. We've seen that before, right? Actually, that was 5, not 4. It was in the wrong column. So if you want to calculate this now, you need to calculate 1 minus 0.9985. And that gets you back to 0.015. But this time you're not multiplying it by 2 because it's not two-sided, you're only interested in that direction. And for the hypothesis testing, I have given you, and please review the slides. I have given you, these slides. Please review these slides with the cholesterol example, because here you see exactly what we just did. So this is a two-sided test. You remember that example with the cholesterol, right? Two-sided test, both sides. Now the next one. Two-sided test, one-sided test. Cholesterol. Mu is greater or equal to 11, which is the population mean. Mu is smaller than 211. Now you only look at one side. And this is why I think it's important. Sorry, I come back to you in a second. And this is why I think it's important to map this out to not mix up, because this is what we just did in the inverse. So that was our step 2. That was our second left-sided hypothesis. Now we're doing the right-sided. It's the same thing. It's basically taking everything under the sun. Yep. Yes.
How is it possible to reject the null hypothesis on one side and not be able to reject the null hypothesis on the other side? Meaning that your p-value on the right side is 0.0000015.
Yeah.
So that would be significant.
That would be significant.
But
yes.
your p-value on the left side is 0.9984, which is not significant.
Because it's directional. Because now you're not testing what is different, which would require both p-values, both tails. Now you're testing whether the direction is true or not. So you're only interested in one direction. You're only interested in that critical, that calculated set, and everything above that.
Right side, or what is this graph showing?
This would be right-sided, yeah.
Right side, 'cause you're not.
So your null hypothesis, so your null hypothesis actually is everything smaller than that. Whereas your alternative hypothesis, this is what you're testing, right?
And what can you say that your conclusion would be? You can reject the null hypothesis?
Here you would not reject the null hypothesis because your p-value is really large.
In our
That's our second example, yeah.
For the right side, if you would.
Yeah, so this is a different value. This is negative value,
Yeah,
right?
but that's not, but I'm saying for our example right now, the
Yep.
conclusion would be you reject the null hypothesis.
Not in the second, not left-sided,
Right.
but only right-sided. Okay? All right, so I will post this Excel spreadsheet in these calculations, but keep this in mind. You have it now recorded. I walked you through this analysis and this calculation. You need to follow this very rigorously in the way I've explained it to you now. But it is, you will be able to get through the logic of this. It's not difficult. And there's a second example, but we don't have time. We only have 12 minutes left. So I will need to jump now into the practice lab to make sure that you know how to do that. So the second example essentially is, just to briefly give you a taste for it, it's basically,
submit the Excel sheet, or we're just doing the R?
you don't need to do the Excel sheet. I will post the Excel sheet for you. But I think it's important that you walk through that. Really do the exercises. Do these exercises that I post. It's really is going to help you. Because there were reasons why I picked these examples, and then I'm giving you these examples. It will make sense. So this is basically the same situation. This is the same calculation. It's basically it's boilerplate at this point, right? You know exactly how to walk through it. It's and to be honest, it's like that's the beauty of statistics, because you have a general principle that you employ to do things in a certain fashion. And once you understood the standardized approach that is being used, you can basically tackle every challenge that comes your way. That is actually, so there's no deviation from these principles, right? It's the same principle. Once you have the principle for one example, you can employ it to others. The key of statistics in general is to know how to utilize the methods. And this is nowadays with programming languages like R, Python, whatsoever, SPSS, or whatever you want to use, super easy. The real challenge in statistics is to know how to employ them to which data. And that's the key. And this is why I gave you basically the same example, and you can try this yourself. Try it in Excel, compare it to the results that the R code is generating for you, walk step by step through the R code and compare it to what you're calculating. And now 10 minutes are, so it's not enough time. But yeah, okay, so the R code, just start your R Studio. It's basically the calculation that we just did, right? It's super simple. And it basically shows you, it's like R, you can use R as being nothing else than a super sophisticated calculator. And that's what we're doing essentially, right?
If we don't finish this today, are we going to finish it on Wednesday? If we don't finish this today, are we going to finish it on Wednesday?
Oh, we will finish now. I just walk us through. This is.
How do we run the code? I forgot how to run the code.
Control Enter.
Control Enter.
Control Enter. So you basically, you just use this R code. It's like I told you from the beginning, I will not teach you how to code R with an SMS. It's practically impossible, right?
Maybe Control Enter from line 1.
You can just go through with me. So you come through that code. You are calculating with every step.
Can you do this one?
With RM, line number 2. Are there questions?
How do I undo? How do I undo?
Just go back up.
No, like I did Control Enter, but I'm not doing anything here.
So there's no undoing. Okay, so Control Enter in line 2 cleans your environment. So this needs to be blank here, right? So if you click now on line 5 and you do Control Enter on line 5, it will assign to a variable mu the value of 500. If you press Control Enter on line 6, it assigns 100 to sigma. Line 7, 542 to x bar. Line 8, n equals 50. And on line 9, it will utilize these for on line 9, it calculates standard error of the mean based on these assigned values. Can we please focus on one conversation only? Thank you. Line 4 is assigning, that's nothing, it's commented out. The hashtag is in comment. The hashtag in the beginning of line 4, you don't need to run it. You can run it, it will do nothing. It's just a comment. Yeah, you just Control Enter, you go line by line by line.
When I do that, nothing else. What is control enter? I don't have enter.
You have return, control return. Control. So control return, not control enter. 12. On line 12, you're basically calculating the set. You need to go to the video then. So you go line by line by line down to. Just follow along with me. Just follow along with me. So you're basically calculating here step by step using the same formula that we have now calculated in R. You're doing the same exercises. These are the same formula that we have put into R, except for this one, that's actually an estimate of the p-value. That's how you would estimate the p-value in R. So the only thing you need to do, you go in the respective line, you press control and return on a Mac or enter on a Windows computer, and you basically run every line. Yes. No, just go. You can do every line. You can also do it in one. It doesn't matter. Control A, Command A. Command A as Adam. Yes. Like this. You can run it like this. That's your practice lab. Command A, you select everything. Control Enter runs everything. You can clear. It will automatically clear everything. Okay. So I got 4 more minutes, then you can chat. Can we focus? Excuse me, ladies. Can we focus? Okay, I just want to walk you through this code for a second more. So you have here every step of this. Excuse me. Can we focus? Okay, so you have with every line, you have the calculations that we just did in Excel. You have the one-tailed, left-sided analysis here. You get that p-value that you needed for that calculation. You have all of these calculations here at your disposition. So you can calculate all of this through in the same fashion. You have the 95% confidence interval here. And you can do all of this easily. You do it line by line by line, and you can use R to confirm your calculations. If you want to play around with the exercise in Excel, you can confirm your calculations by using the R code.
So I just click enter.
Well, you can press Control A and run it through, yes.
I'm confused. I'm just at the beginning. What do I do?
Control Enter.
What does that mean? So I was doing that and then it ruined the whole
Yeah, so yes, so this is basically running the code. If you press Control A, this is hearing you about your entire environment. So now you assign things to your environment here on the side. You see that? And now you Control Return. Yeah?
Okay, so when? When do I do that? Or
all the way down. Yeah. And that put in a text document and submit for practice lab 2. You select all of it in the console. Okay, ladies, 2 more minutes. Yes.
And then, like, submit this for the environment all the way to that.
Exactly. I'm going to show this again. Okay. Yeah, but this is the second example. You have 2 examples in there. Okay, everybody to their seats, please. I want to make some general announcement for the last 3 minutes. Okay, we need to. later. Okay, so what you need to do, can we have the screen? Sorry. Okay, so if you click in the console, go in the console, press Control and L, delete everything in the console. You click now in the script, just follow what I'm saying, please. You go in the script, you press Command and A, and you press Control and Return. This will run the entire script. Then you can select everything that is here, and this follows the same layout than we did for practice lab 1. You press now Command and C, and you start the text editor. And in the text editor, you will copy everything that you have selected in the console. You create a new document, and you copy all of this in the text editor. Okay?
What do you press after you do Command A? What do you press after you press Command A?
Control Enter or Control Return. Yes.
Like when you're doing the return for the top, it kept resetting the values.
Yes, yes, yes.
You need it down and then, like,
Yes, because there's a second exercise in there. So there are 2 exercises. So both exercises that were posted as practice lab, there are 2 separate exercises. The solution for both of these exercises is contained in this code and will be contained in the Excel spreadsheet that I will be sending you as an announcement.
no, but is it fine that like I was doing the entering and then for the values, it just like delete all of them and then it reset and it started doing new ones, so they're not all there.
Again, it's the second exercise. That's why I deleted all of the values. That's the second exercise. You're meant to actually study that code if you're interested in it, because it basically gives you an accompanying value for the exercises in Excel. So this is for you to practice the calculations in Excel or on the calculator, whatever you want to do. This is meant to help you with solving exercises like that. You actually.
What should I delete? I should delete from clear the environment. Like I should go here and up and delete.
No, you just press Control and L. What is this? Oh, that's the text editor.
This is script editor, right? This is the one that worked last time.
You want script editor? Okay.
Editor.
Text edit.
One of them didn't work last time, remember?
Yeah, last time we did text edit.
I should do text edit.
The text edit.
Text edit.
Yeah, that's just create a new file, new document.
Document, okay, now.
Copy it in there. Yeah.
What time do you do Command A?
Command and A selects the entire script.
On the bottom left? Or the console?
No, you first go. Okay, once again, you go in the console.
Yeah.
You press Control and L. You clean everything. You need. Don't look at me. Don't look. Excuse me. We need screen. Control L deletes the console. Command A. If you click in the script, selects the entire script. Then you press Control and Enter. Runs the whole thing, and then select everything.
Okay.
And copy that in the text editor.
I don't have a text edit on my computer, so I just do like folder.
You have, yes, you can do it in a text file.
And then
Just make a right click in a folder, then you can go on new, and there's a text document that you can open.
and then
That's fine.
and then how do you save all of that? Like how
In a text file.
but the text so I'm just posting the
Yes.
text edit.
Yes.
Oh, okay.
Just rewatch the video. Just rewatch the video. It's going to be on the video how to do it.
That's the small part. This is all I'm posting.
Yes, I don't see that far, but yeah.
So I put on the right one now.
Okay.
So where do I start from? Should I
So
delete the
now
top?
you save it.
I'm just done. I say,
Now you save it, and that you submit.
I should title it our first name and then.
Yes, please put in the course label, First name, practice lab 2.
Thank you.
Hmm?
Did you say that there were 2 examples?
Yes.
So we have to do 2 of these?
Yeah. No, it's in one code.
Oh, it's in one code?
It's in one code. Yes.
So that's why it's confused between standard error and standard mean. So just screenshot from the textbook or
Yep.
sorry, am I not talking about that? Okay. I was getting confused between standard error and standard mean. Because in the textbook it said therefore.
Wait, hold on. Let me stop one of this. This is.